Imagine Earth as a living canvas, splashed with shifting colors and moving continents, oceans like vast brushstrokes breathing life into the planet. Now slide the clock back 486 million years and linger there for 41.6 million years. You have arrived in the Ordovician, a world both alien and surprisingly familiar, a time when oceans reigned supreme, life flourished in unfamiliar shapes, and the stage was set for one of the planet's great extinction dramas. This is the story of the Ordovician, its landscapes, its life, its climate swings, and the cosmic and earthly forces that shaped a chapter of deep time. Think of it as a long-form nature documentary, narrated through the voice of the planet itself. The name Ordovician comes from a hill country in Wales and a forgotten tribe called the Ordovices. In 1879, a perceptive geologist named Charles Lapworth looked at rocks that didn't quite match the Cambrian below or the Silurian above. Instead of forcing them into either category, he gave them a new home, the Ordovician. 40 years after his death, the world finally agreed. The name stuck. The period stretches from 486.85 million years ago to 443.1 million years ago, a tidy slab of time in which oceans deepened their complexity and life pursued new experiments. Paleogeography during this period reads like an artist's map of drifting continents. Gondwana, the supercontinent made of today's Africa, South America, Australia, Antarctica, India, stretched from near the equator down to the South Pole, a bottom-heavy colossus wrapping much of the southern hemisphere. Laurentia, the core of today's North America, Baltica in northern Europe, Siberia, and smaller players like Avalonia drifted well apart from Gondwana's embrace. Panthalassa, a single massive ocean, dominated the northern hemisphere, a watery expanse that covered more than half the planet. These separations mattered. Oceans created isolated pockets of life, evolutionary theaters where unique casts of organisms evolved distinct looks and lifestyles. Avalonia rifted from Gondwana and drifted northward, later colliding with Baltica and closing the Reich Ocean between them. Mountain building did occur, but not by giant continental smashes so much as by volcanic arcs and microcontinents accreting to margins. The tectonic orogeny stitched together the Appalachian story, island arcs stitched onto Gondwana's margins. Subduction zones hummed along ancient shorelines. Volcanism erupted. A massive ash deposit around 454 million years ago was one of the biggest eruptions in 500 million years, and yet life barely flinched. Seas were the defining habitat of the Ordovician. The world was a place of calcite seas, where low-magnesium calcite dominated how shells and hard parts were made. Where Cambrian seas had been dominated by microbial calcite, the Ordovician saw animals, brachiopods, bryozoans, corals, crinoids, nautiloids, take the lead in building calcium carbonate structures. The chemistry of seawater favored calcitic skeletons and hard grounds, cemented seafloors where life made its stage, and where the traces of tiny borers and encrusters tell stories of bustling communities. Climate in the Ordovician was not a single static mood, but a series of moods. The early part of the period was very warm, a greenhouse world, with carbon dioxide levels far higher than today. Sea surface temperatures rivaled those of the early Eocene, a time of lush warmth, but the planet cooled through the early into the middle Ordovician. Humidity shifted. Oceans and atmospheres danced through humid pulses, temporary warmth and cooling trends. By the Sandbian and into the Cadian, Earth flirted with the first stirrings of long-lived ice, the early Paleozoic Ice Age, and by the Hernantian, the end of the Ordovician, an icehouse episode gripped Gondwana as it drifted over the South Pole. Sea levels rose to heights rarely seen in the Paleozoic and later plunged as glaciers grew, carving ecological futures with their advance and retreat. And life. Oh, life. If the Cambrian was the time of first dazzling experiments, the Ordovician was the era of refinement and expansion. The Great Ordovician Biodiversification event sent biodiversity surging. Marine genera quadrupled. The shallow shelves bloomed with life arranged in tiers, filter feeders sifting plankton, predators lurking, encrusters building communities on hard substrates. Invertebrates dominated: mollusks, arthropods, brachiopods, bryozoans, corals, and echinoderms filled every available niche. Trilobites, iconic from the Cambrian, diversified into exotic forms, some armed with spines and nodules, others developing eye stalks or losing eyes altogether. some evolving to swim with streamlined bodies. Trilobites remained abundant, but were joined and sometimes overtaken by articulate brachiopods and other forms better suited to the New World. Cephalopods, the nautiloid ancestors of squids and octopuses, were expanding into every marine zone, becoming formidable predators. Mollusks diversified into bivalves and gastropods, many taking advantage of the calcite seas to build strong shells. Graptolites floated through plankton-rich waters, widespread monitors of oceanic life. Crinoids and cystoids, relatives of starfish and sea urchins, anchored to the seafloor like underwater trees, their feathery arms filtering food from currents. Corals began to form reefs in earnest, and bryozoans spread into delicate, lacy colonies that encrusted shells and rocks. A remarkable shift was happening in the feeding strategies of the oceans. Filter feeding exploded. A gigantic filter-feeding radiodont called Edgerocasus roamed Ordovician seas like a living manta ray, straining plankton through wide appendages. The Ordovician established food webs more complex and efficient than those of the Cambrian, with shorter food chains and richer biodiversities. At the same time, miniaturization occurred in several lineages. Some groups evolved smaller forms, perhaps adapting to more specialized niches. Biogeography mattered. With oceans separating continents, marine life showed strong provincialism. Different continents hosted distinct trilobite groups. Tropical Gondwana hosted its own assemblages, while Laurentia and Baltica favored others. Over time, as seas shifted and oceans narrowed, these provincial boundaries blurred. Beta diversity, the degree of change in species from place to place, declined as taxa dispersed more broadly. Yet even into the late Ordovician, islands of uniqueness remained. On land, the story was quieter but profound. The first plants, small non-vascular liverwort-like organisms, pushed beyond tidal edges into moist soils and rock crevices. Tiny spores preserved in sediment tell of early bryophyte-like life colonizing the land in the middle to late Ordovician. Fungal partners, likely early mycorrhizae, entwined with plant roots, helping plants access nutrients, a silent alliance that would become a cornerstone of terrestrial ecosystems. Arthropods, too, began the tentative step onto land. Molecular clocks suggest early arachnids crawled onto shorelines by the end of the period, starting the long story that would eventually populate continents with terrestrial animals. But the land remained low and sparsely vegetated. Shorelines and damp pockets were the primary terrestrial habitats. Beneath these scenes lay the slow, patient work of geology. Tectonic stitched and unstitched landscapes, volcanic arcs accreted to continents, and the pattern of rifting and compression reorganized ocean basins. The Ordovician saw both quiet interiors and violent margins. The ash of a massive eruption, the Milberg Big Bentonite, settled across vast areas at around 454 million years ago. The rock record hides wonder after wonder. Limestone layers packed with fossils, hard grounds marked by the graffiti of borings and encrusters, and shale beds that preserve fine details of soft-bodied life. The Ordovician also bore witness to an unusual celestial chapter, the Ordovician meteor event. In the Middle Ordovician, around 467.5 million years ago, the L chondrite parent body, an asteroid or small planetesimal, broke apart, spewing fragments into the inner solar system. For a period, Earth endured a higher influx of meteorites, perhaps 100 times the rate of today. A 2024 study suggested these impacts clustered in a band around Earth and proposed the intriguing idea that the breakup formed a transient ring system. Debris raining down from that ring might have peppered the globe for millions of years. These impacts are not tied to mass extinctions, but they add an extra note of drama to an already dynamic age. The end of the Ordovician brings us to a dramatic finale. Between roughly 447 and 444 million years ago, life faced a crisis. This extinction, the second largest in terms of genera, lost roughly half of marine genera. Brachiopods, bryozoans, select trilobite groups, graptolites, and certain cephalopods were hit hard. The most widely accepted culprit was climate change. As Gondwana drifted over the South Pole, ice sheets formed. Sea levels dropped as water locked into glaciers, shrinking the vast shallow seas that harbored so many organisms. The drop in sea level eliminated countless habitats and forced surviving organisms into smaller refugia. The cooling was preceded by a significant fall in atmospheric carbon dioxide, from perhaps 7,000 parts per million down to around 4,400 ppm, a drawdown possibly driven by enhanced weathering of new silicate rocks or by the colonization of land by plants and lichens, which accelerated rock weathering and pulled CO2 from the atmosphere. A cascade of feedbacks tightened the planet's climate. Glaciers grew on Gondwana's southern reaches. Sea levels fell for roughly 3 million years, then fluctuated in pulses as glacial advances and retreats occurred. The extinction appears to have worked in waves. Tropical species were hammered first as warm, shallow seas contracted. Cooler water species suffered later when different conditions prevailed. Yet extinction is not the end of the story, but a pivot. Life that survived the pulses went on to radiate and fill emptied niches. The oceans became different. Sometimes deeper oxygenation followed glaciations, allowing new benthic communities to colonize deeper waters. A pattern of Lazarus taxa emerged. Organisms that seemed to vanish from the fossil record during the crisis later reappeared in the Silurian, suggesting they persisted in hidden refuges until conditions improved. Scientists have debated alternate triggers: a brief gamma-ray burst, catastrophic volcanism, or the effects of a temporary ring system that might have altered sunlight reaching the surface. The evidence converges most strongly, however, on climate-driven change tied to CO2 drops and Gondwana's polar migration. The extinction's duration remains a subject of study. Some work suggests a relatively quick event in geological terms. Others argue for a protracted crisis with multiple pulses. As the Ordovician closed and the Silurian dawned, the stage had been reset. New reef systems took hold. Brachiopods and crinoids adapted and diversified, and the evolutionary experiments of the Ordovician fed the long story of life in the seas. The roots of terrestrial ecosystems were planted, tiny and unassuming, but crucial for future terrestrial forests and the animals that would follow. What remains for us now are fossils and rocks, snapshots of a world long vanished but not lost. Hard grounds pocked with borings record the industriousness of minute miners. Limestone beds hold the shells of brachiopods and corals, telling of warm, shallow seas. Graptolites in black shales float like ink blots on ancient ocean surfaces. Tiny spores whisper of the first land plants. Meteorite fragments embedded in layers tell of cosmic connections. Each line in the rock record is a sentence in Earth's autobiography. The Ordovician feels like an elegant middle chapter. After the experimental bursts of the Cambrian, it refined, structured, and multiplied life. It stitched ecosystems into layered complexity, ennobled the role of calcifying animals, and set the scene for future chapters, the Silurian and Devonian, when jaws, forests, and terrestrial ecosystems would play larger roles. Its end, abrupt and harsh, was a reminder of planetary vulnerability. Climate shifts, sea level changes, and even cosmic events can redefine life's trajectory. So when you next look at a seashell, imagine the Ordovician ocean teeming with relatives of its builders. When you find a fossil in a limestone slab, picture a shallow shelf where currents moved plankton through the arms of crinoids and where tiny borers etched their lives into hard grounds. The Ordovician is both distant and intimate, a world that shaped the chemistry of seas, the architecture of marine life, and the very pathways that led life from ocean to land. In the grand story of Earth, the Ordovician is a reminder of resilience and reinvention. It shows how life can diversify dramatically, how ecosystems can be assembled from countless interactions, and how fragile those systems remain in the face of planetary change. It is a chapter of deep time with clear echoes for us today. The planet's climate systems, seas, and life are intimately linked, shifts in one ripple through the rest. The Ordovician's lessons are ancient, but their resonance is unmistakably modern. Ambient music swells, then fades into a gentle, contemplative hum. This was the Ordovician, a luminous, tempestuous canvas in Earth's long gallery. Thank you for listening to a story written in stone, told by the fossils and sculpted by time.